Thank you everyone for coming. I work at the SETI Institute as an engineer. I wear many hats, but I primarily work at the ATA, the Allen Telescope Array in Northern California. And I'm here today to talk more about our next generation Allen Telescope Array processing compute pipeline developed together with NVIDIA, represented today here by Adam Thompson. So starting up, so for some of you that don't know what SETI is basically the search for extraterrestrial intelligence. It's basically searching for any signs of intelligent life in another planet. And we did this just by employing very, very fancy technology, sifting through noise and trying to detect any signal that resembles something that can be intelligent, like a drifting line on terahertz of noise. But yeah, our mission is to answer if we are alone here, if we are only intelligent species in the world. That seems unlikely. And one nice equation that became the staple of SETI research is the Drake equation right in the bottom there that quantifies the possibilities to find extraterrestrial life in the universe. And yeah. So the Allen Telescope Array is an array of dishes at Northern California. We have currently 42 antennas, and working with the refurbished feed, that is a better upgraded feed, we have 28. So that was from 20 from the beginning of this year. So we increased our capabilities for almost 50% just in 6 months, and we are also working to upgrade even more of the feeds to the new generation cryogenically cooled counterparts. So in summary, each antenna produces 1.5 gigahertz of data per polarization, and that equates to 3 gigahertz per antenna. And if you count all of the antennas, you have 84 gigahertz of data that has to be processed in real time. And that's a very large amount of data because that aggregates into 1.5 terabits per second and at 8 bits per sample that we sample at. And all of these is connected to a central on-site processing room that it's composed by servers and also FPGAs. And one key difference from the Allen Telescope Array that it has ultra-wideband reception. So we are sensitive from 300 megahertz all the way to 12 gigahertz. So it's pretty wideband and quite unmatched from radio telescopes. And a data acquisition is basically the RF SOX bars for Xilinx. So the ADC is integrated with the FPGA itself. So the incoming data comes from RF over fiber, and then it's digitized. There is a large polyphase filter bank, and then the packets, UDP packets, are sent to our compute nodes over 100 gig networking switch. This is a diagram of the operation. So we have the antennas, we have the analog clusters composed of LOs and amplifiers. Then it goes to the RF SOC boards where the samples are digitized and sent over our digital processing cluster. So our production pipeline uses this piece of software called HP Guppy. That is a CPU-based UDP receiver. So all the UDP packets, like 12 gigabytes of data incoming to the server, needs to be copied to system memory. And since we do the processing using Blade, another framework for processing, all the samples needs to be copied again to the GPU. So it's basically a bounce buffer on the CPU. So not much efficient as the current production. So I will talk a little bit more about Blade to make sure we are on the same page. So Blade is an acronym to Breakthrough Listen Accelerated DSP Engine, but it's actually an excuse for me to put more Blade Runner references to the code base. So Blade is responsible to do the digital signal processing at the ATA, and currently in the Cosmic initiative on the VLA, We also use Blade in the VLA, and we are trying to expand more at more observatories. So its job is to process that 1.4 terabits of data that I mentioned earlier, and that equates for instances. We have 16 instances, and each one of them are processing 90 gigabits per second per interface. So that's almost saturating our 100 gig network interface. We are looking into upgrading it to something like 200 or 400 in the future, just to increase the processing capabilities of the system. And Blade is just like radio is composed of modules. Each module is like beamforming, correlator, channelizer, cast, some stacking concatenation of arrays. So we currently have 9. Every month we add another one because we need some other type of processing. But the designs of Blade is basically followed by 3 common parameters. So that's a common interface between the astronomy-oriented DSP modules, because many times in astronomy you have a piece of software that is very good at something, but it can't communicate very easily with another piece of software that does another thing very good. So Blade would work as a connection, like a translation layer between the softwares, and we also build our own kernels to do the digital signal processing. Another thing is the just-in-time compilation of the CUDA kernels. So to extract the most efficient way to process things with the GPU, we compile the kernels just in time with static for loops, etc. So that gives us squeeze a little bit more performance from the GPU. So, and also it doesn't need to compile every time. So if you change observation parameters, let's say the number of antennas or the number of channels or the time samples, you don't need to recompile Blade to make it work. So everything's just compiled just in time, just by calling a function. And that's done all transparently from the user, so they don't need to know that that's happening. And also performed while hackable, so we don't need something that will be stuck in time, like many astronomy software. So it needs to be feasible for some PhD level students or even lower to change the code for their necessities. So that was also a constraint of the design. So as I said, modules. This is in the left there, we have an example of one of the pipelines of Blade. So each pipeline is composed of many blocks. So for example, here we are doing the beamforming pipeline. So the signal is received. They are all integer 8s from the telescope, from our SOC boards. They are casted to float 32 as a common interface between the modules. We can go lower, like a float 16 or even lower. But we stayed with 32 for now because computation is not a problem here. And there's a channelizer that you can pre-channelize the data before the beamforming. That's sometimes a requirement for some observations and other blocks, like after the beamforming, like circular polarizations, like you can synthesize circular polarizations. Anyway, that's just an example. You don't need to know about this. So modules, pipelines, and blade runners that will run 2 pipelines concurrently, asynchronously. So you can extract the most performance from your GPU as you can by uploading data to the GPU while you're processing. So you can do this at the same time because they are independent pieces of silicon on the GPU. So you can extract all your money worth from the GPU. And again, all of this is done transparently from the user. User doesn't know that this is happening, but it is happening. So no effortless optimization. So now, Holoscan, the spicy part, the new part about the next-gen pipeline. So just like introduction, Holoscan is a NVIDIA SDK provided by NVIDIA. It's all open source. You can read the code in GitHub. It's basically a sensor processing platform. So if you have lots of sensor processing lots of data, Holoscan can be useful for you to make sense of that data. And it's scalable and also simple. You can use from C++ or Python, anyone that you prefer. But for us, the main advantage of using Holoscan is that we can leverage the power of the advanced network operator called ANO that abstracts away the GPU direct RDMA part of the process of receiving the UDP packets from the FPGAs into the GPU memory. So whenever we receive UDP packets coming from the FPGAs, ANO will automatically, everything is programmable on a YAM file, so it's very easy to modify for your needs. So the UDP packet arrives. You can tell the header offset of that packet. So ANO will strip the header out, store in the CPU memory, so you can know the metadata of that memory, and then get the data of the packet and upload directly from the network card directly to the GPU without going to the system memory. So it looks silly, but it's a very, very efficiency gain because, for example, if you have a system with two or more GPUs, that becomes very important because if you have 4 Mellanox cards copying data at 12 gigabytes per second to your system memory will be bottlenecked very fast. And also your CPU cards will be busy doing the bounce buffer. So what Holoscan does is to copy directly to the GPU. So your CPU is never involved into the process. Your CPU is just a memory management. It will never see a piece of data. It only will see metadata from the data and out doing the memory management of the process. So it's much more efficient. It lets you to spend less on CPUs and more on the GPUs where the data is processed. And this is an approach where we can replace HP Guppy, the CPU-based one that gets the packets, with Holoscan and get our older DSP framework into a Holoscan operator and have the efficiency gains while maintaining the processing power from Blade. So, and this is, so it's crucial to think about this, like your packet is coming from the network card, it's transferred directly to the GPU. Your GPU will receive it, will process it, do the beam farming, and other processes, channelization, and then it will be either processed further. For example, with Holoscan, we can use a machine learning model to run inference in real time. So the data is reduced to a single beam from the 28 antennas into a single beam, and then with the beam farmer, and then analyzed using the machine learning model. Or you can store the file directly to disk using the GPU direct storage. So your CPU will create a HDF5, for example, file, header with all the metadata, and tell your GPU to write the data that was just processed to that address on disk. So again, CPU never sees any data. Everything is RDMA'd around, and that's and you won't be bottlenecking your PCIe switches or your system memory. And a good aspect about the ATA is that we can do whatever we want with the telescope because it's owned by the SETI Institute. So we have a history of getting things more efficient as possible. So when I started, 2 years ago, we had like Blade 0.6.5 that we had like the beamforming, mode B, and then we were analyzing the data. And to analyze the data, we had to channelize it. It's basically do a FFT of the whole array. So that's 3 gigahertz of data being FFT'd every second. So with Blade 0.7, we were able to not write the raw data to disk and do the channelization online, and that saved us like half of the PCIe hops. So that decreased latency and also the PCIe utilization. But the next step of this optimization process is to get rid of the CPU bounce buffer, and that's why we are using Holoscan for this. So we can copy the data directly to the GPU, and again, we will have just as half of the PCIe hops. So comparing from 8 CPU hops in the beginning to now with just 2 PCIe hops and 1 NVMe write. We did some testing with our new Shiny pipeline, and here we were using CyberEther. If you want to know about CyberEther, go to my next talk this afternoon. So the data was being received by Holoscan, transferred to Blade. Blade was doing the beamforming, and the final data was being plotted by CyberEther on screen. This was running 100% on the ATA on a server. CyberEther was working on a headless mode, and the frame buffer of Blade of CyberEther was being transmitted to my local machine. At the time, I was in Brazil, so this traveled more than 12,000 kilometers with acceptable enough latency where I could control it. And the transmission was only like 10 megabits per second instead of 12 gigabytes per second this was processing at the time. So for testing, we pointed the telescope to Mars, and we beamformed into the planet. And when we did that, we saw 2 peaks on the left there. And this is the X-band for reference. So one of those peaks was Mars Odyssey, orbiter in Mars, that you can see the peaks there. It's a phase modulation. So there's a prominent carrier wave in the middle there. You can't quite see the side lobes here in this recording. And also the other one was Tianwen. That's another, that's a Chinese orbiter in Mars also. So yeah, well, the new pipeline with Holoscan did work for us in this test. And also, we pointed to geostationary satellite called GOES 16 and 18, and we also saw the signals. And even with the new mode, that is just a contiguous 16 megahertz bandwidth, wide with no polyphase filter bank, we could see it without the little creases there. And also, non-space demonstrations, we pointed this to the nearest city and saw the thing getting crazy with Wi-Fi apparently and LTE downlinks beamforming to a city. And with the GOES data, we were able to download these images from the satellite with the new pipeline. So the data, the raw data was beamformed and then stored to disk and then later processed by some open source software. So we were able to get some of those images. As future for this pipeline, we are building new software called Nexus, another Blade Runner reference, that will so we have many instances running at the same time of Holoscan, and they need to be synchronized. So they all need to tell the head node or Nexus in these circumstances that they have X timestamp, and Nexus needs to decide where to start, when to start to record. So it will, all the nodes will report a timestamp. Nexus will decide that, send a timestamp where the recording is supposed to start to all the instances. And once the instance see the packet timestamp, the recording will start. So all of them are coherent, and we can analyze the data knowing that they are coherent between instances. And Stellene, also another Blade Runner, that it has a holoscan. Stellene is basically a superset of holoscan with extra operators that we use at ATA, like the transport that we have, the reshuffling of the packets. Our headers are different, so it doesn't make sense to put in holoscan. So we have Stellene that's a superset of holoscan, and holoscan calls Blade for the DSP when necessary. For future, we have very big plans with holoscan, this new pipeline with holoscan. So we plan to receive the packets, do correlation or beamforming. We can also do both at the same time if the observation requires that. And after the observation is done, we can either do the Doppler search that will check for drifting signals in the spectrogram, or do visualization like I just showed you with CyberEther. And more excitingly, we can do real-time ML inference. So that's not recording data to disk for later analysis. This is literally analyzing the data as it gets in. So if you have low enough latency and a very clever circular buffer of your raw data, you can beamform the raw data, run the inference, detect that there is something in there, like a drifting signal, a fast radio burst, and then you can tell the circular buffer to dump the timestamp A to B, so you have raw data of the event, so you can do further localization of that source, because with the raw data you can steer your beam and find out the more properties about that burst that we wouldn't, data that would otherwise be lost with the beamforming, because the beamforming is the lossless operation. So you can get the raw data and do more analysis, and scientists will be happy. We are testing our new compute platforms. One of them is the IGX RN. That is basically ARM RN, like a Jetson, coupled together with a ConnectX that serves like a PCI switch. So we have 32 PCI 5 lanes, and 16 of these lanes are used for a 86000 card, or a 6000 ADA. And the other ones are connected to the ARM cores. So the data comes in directly through the ConnectX and goes to the GPU. And this is important because we need rebar. We need to map the VRAM more than 256 megabytes at the time, because we are processing 12 gigabytes per second. So we would have less than 16 milliseconds to process everything, and that's too low. So we need more of that. So our systems needs to support PCI resizable bar. That's not a tough ask, because the standard, it's on the standard since PCI 3 that was released in 2012. So that's more than enough time for integrators to implement it. But Supermicro didn't get the memo and just implemented the resizable bar in the last generation servers with AMD Genoa. So we need to replace all of those servers to use this. If you have any questions, I will be here all week. And I also have an email. You can contact me there. Thank you very much.